Hello. We talk about wave propagation in periodic structures. We will be dealing with crystals and we will be looking at the wave properties of particles when they travel along a crystalline structure. So it's important that we look at the general attributes of waves in a medium which is made of discrete periodic structures. So when we talk about periodic structures, we are basically talking about crystals. There are a few properties by which we define a wave. If you think about it, a wave is composed of a wavelength, lambda, which is the which tells us how what's the distance for the repetition of that wave. We have angular frequency omega, which we measure in terms of 2 pi times frequency. So angular frequency in terms of frequency is 2 pi v, which we are using for frequency here. It's another important property which is called phase and intensity. So intensity is the square of the amplitude of the wave. These are basic properties of any wave. Now, when a wave travels, we want to know what is the speed of the wave. The speed of the wave is measured just like we know speed. It is a distance traveled in unit time. So in our case, this is the uh, lambda times frequency. So this is the velocity. For now, frequency we know is 1 over second. So it fulfills the requirement. Now, instead of wavelengths, we can also describe a wave in terms of its vector, k. So this is something which we'll be using a lot, k vector or k space. We will be translating things into more into their wave form or wave properties than the particle. So when we do that, then we are interested in the k-space properties or the wave vector properties. So when we describe it in terms of the wave vector, then that is 2 pi over lambda. So k would be, what we will be using would be 2 pi over lambda. So these are basic relationships. Now, when we talk about single velocity, single wave, then we talk about the speed of the wave, but then there are a bunch of waves which are traveling, then we talk about the phase velocity of the wave. So that's written as omega over k. Now, we when we talk about a bunch of waves, we are talking about a wave packet, which is basically a bunch of waves which are superimposed on each other. Now, the wave packet is where then we use group velocity. So in that case, the definition is Vg, which is now group velocity. It's ratio of the wave vector with respect to the k space. So we write d omega over dk. Now, when you think about a plane wave, there are uh, it's a periodic thing which propagates, let's say, in plus minus x direction. So in that case, we have the relationship that we can write for uh, the plane wave. In that case, we would write it as a psi. And when you defined a wave vector, then we have to find out the equation for the wave vector also. So wave vector psi is then uh, for a plane wave in plus minus x direction. It can be written as the amplitude times exponential to the power of j k x plus omega t. So this is a factor which is dependent on the phase the amplitude, and time. So all those things that then go into defining a, a plane wave, which is propagating in plus minus x direction, one direction. Now j is the imaginary part here. Now, and the presence of k in the exponential tells us that this is the plane wave written in the form of a wave vector k, and that's what we'll talk about when we talk about uh, particles and their movements. Because in a crystal, the most important thing for us to know is that how particle, if a particle moves from one atom and it's traveling in any particular direction, the direction makes a big difference. Because if it's going in 111 direction or 100 direction, in both cases, how quickly it encounters another atom would be different, because the distance between those atoms would be different. Now, if we have bunch of waves that are traveling, like we were talking about the wave packet, then we can take the linear combination of all the plane waves and we can write them in the form of a standing wave. Now, standing wave is a concept in communication that we deal with, that if there is a, a boundary condition applied, which means the crystal is not infinite, but it's finite, which is the reality. The waves can be taken in a finite distance. In our case, we take lattice constant, which makes it easy for us. Now, if they are traveling in a lattice constant A, the length would be then NA, where N is the number of atoms. X number of atoms, if they come in within that region, whatever the finite size we are taking. So we can write the length as NA, where N is the number of atoms and A is the lattice constant. Now, the plane waves, when they reach a finite end, they would bounce back. So there'll be a back and forth, they reflect back. So there's a back and forth, what we call as the creation of standing waves. Now, this reflection turns out that it helps us mathematically deal with that wave, or that in of, the, of those bunch of waves that are superimposed. It becomes easy for us to deal with that than if we had an infinite crystal. So, but even if we have to deal with the infinite crystal, we take the finite solution and we can just apply it over the whole medium, over the whole bulk of crystal. So, but if you were to deal with realistic system, then this would be the case, as is shown in 1.18a here. So essentially, there are a few conditions that we would apply, that if the atom is traveling, and this can be bunch of atoms traveling, but they would be traveling with the same wave, and these can be not just one wave, but a bunch of waves superimposed on each other. So at any time we can pick up a location and we have a probability of finding an electron over that path for that wave when it's traveling. Now, when you do that, we can uh, take this system and be able to look at bunch of waves which are superimposed in each other. A concept which is called indistinguishability of a wave and a bunch of waves. So which will lead us in our analysis that we talk about one wave, but that one wave may be composed of a bunch of electrons that are traveling. So that one wave is a representative of many charge particles, or charge carriers, electrons or holes, that we'll be talking about. Now, in crystal, the wavelengths are thus physically distinguishable only to some extent, as it's shown in second one. All we are seeing is some superposition where some waves are constructively helping each other, or destructively helping each other. But we cannot distinguish one a wave from another. What we see is a net result. So we will be, when we talk about k-space, we will be talking about one wave. But rest assured, there'll be a bunch of waves that will be clamped together in that. Now, when we are dealing with a bunch of waves, the maximum range of k vector that we can deal with, we call this as a Brillouin zone. Brillouin zone is something which we'll use a lot. Essentially, this is a representation of the waves in the maximum range of those waves that we can deal with. It helps us because when we talk in terms of Brillouin zone or k-space, we are taking care of all the waves that are available in that space. So we will be dealing with wavelengths, wave vectors, k, and we'll be dealing them in k-space. Now, if it was a longer medium where the lattice constant almost, there's no lattice constant and it keeps on going and going, then it doesn't hold there. We call that a continuous medium. So a few important things that we are dealing here with is a number of situations basically where we are treating a finite uh, medium, a finite crystal lattice. And in that crystal lattice, we are talking about not just one, but many, many particles and their waves as they are traveling. Now, once we have those particles traveling, we have to deal with their plane waves. And we represent it in terms of this Greek letter psi. Now, when we are looking at real space, we use x. When we look at the frequency or the waves, we use k space. And just like we would define a function f of t, and then we would go in time from f of t to t plus capital T or some time period, in terms of waves, we will deal with wave and then x, which will undergo a distance lattice constant. So it is just a an appropriate way of dealing with waves instead of particles, because all of our treatment of devices will be done in terms of the wave vectors or how those particles will be traveling in this huge periodic structure. So this discussion will continue in the coming chapters as well.